On spectroscopy, just a reminder, you have an NH stretch in the same region where the alcohols are, but the peaks look very different. They're much more narrow, less broad, and they're nowhere near as intense because the polarity of the nitrogen-hydrogen bond is not as intense. Also, you will see a doublet when you have two hydrogens on the nitrogen, and you will see a singlet when you only have one. And of course, for tertiary amine, there are no hydrogens, and so there's no NH stretch. In NMR, the hydrogen on the nitrogen is a broad peak due to hydrogen bonding, and you can get it to disappear with shaking with D2O. The hydrogens that are alpha to the nitrogen absorb in about the same place where hydrogens that are alpha to an oxygen will absorb. In mass spectroscopy, you have alpha cleavage and you have an odd mass for your molecular ion when you have an odd number of nitrogens. This is an IR spectrum showing how you will, with a primary amine, have a doublet, indicating two hydrogens are on there, one for symmetrical stretching and one for asymmetrical stretching. Notice it is nowhere near as intense as an alcohol peak, even though you have two hydrogens on there. This is the reaction that causes the hydrogen peak in NMR. The hydrogen that is on the nitrogen will disappear when you shake it with deuterium because there is deuterium exchange. And so you no longer will see that hydrogen that's on the nitrogen in the NMR spectrum. This is a spectrum showing you how the hydrogens that are the hydrogens that are adjacent to a nitrogen will absorb in the 2 to 3 part per million range. In carbon-13 NMR, the most important thing is recognizing symmetry reduces the number of peaks. So this spectrum has, the spectrum of this compound would have only 5 peaks because there are only 5 different carbons. Notice that the farther that the carbon is from the nitrogen, the more downfield, the more downfield it is. Notice that this carbon is more upfield than this carbon. Why? Because there are hydrogens on it that are nowhere near as electron donating as a carbon. They're less electronegative. Odd number nitrogen give odd molecular ion if it's present. Alpha cleavage, remember that alpha cleavage does not mean that the carbon-nitrogen bond is broken, but you go down to the carbon that the nitrogen is on and you cleave the bond adjacent to it. Remember that it is only the charged ions that are detected, so that would be the ion that has a nitrogen on it that is stabilized by the non-bonding pair on the nitrogen. This is showing a spectrum so that you can see alpha cleavage in action. The molecular ion has an odd mass, 87, because it has only one nitrogen. Alpha cleavage right here, you lose 15, a mass of 15, and that gives you a molecular, M/Z peak at 72 because you lose a free radical, a methyl free radical. When I lose this ethyl free radical, I get a mass of 58 AMU right here. Why is it that the 58 AMU is greater probability than the one at 72? Because this ethyl free radical is more stable than a methyl free radical. These two things have approximately equal stability, but the methyl is less stable than the ethyl free radical. What reagents are needed in order to get a Hofmann elimination of this amine? Well, first thing you need to do is alkylate this until you get the quaternary ammonium salt. That would give you, you would use something like methyl iodide and use an excess amount of it. Then you would use silver oxide to do the elimination. Silver oxide and the methyl iodide would give you elimination to the less substituted alkene. What classification does this amine not fit? Well, is there a pyridine ring? Yes, this is pyridine. Is there a secondary amine? Well, this nitrogen is secondary. Is there a heterocyclic amine? Yes, this is heterocyclic and it's aromatic. An aromatic amine? Well, yes, this is aromatic. An aliphatic amine? Well, there is no alkyl group on any nitrogen here, so that is the one it does not fit. What is the IUPAC name for this? Well, you find the longest chain, and that would be the aniline. So you would call that aniline, and then we see there is an ethyl and a propyl. So it would be N-propyl, N-ethyl, N-propyl aniline. When nicotine is treated with strong acid, what forms? Well, protonation is going to occur. Where is protonation going to occur? On this nitrogen or on this nitrogen? Which one's more basic? Well, this is an sp2 non-bonding pair. This is sp3. This is more basic. So this compound will be, this salt is the one that would form. List from strongest to weakest base. The strongest base is the one that is going to have the nitrogen non-bonding pair with the most electron density, because the methyl is electron donating, C would be the strongest, and because the nitro group is electron withdrawing, B would be the weakest, so it goes CAB. Which way does equilibrium lie? Well, let's look at this. Which is a stronger base, the amine or the alkoxide? The alkoxide is much stronger, so equilibrium lies to the left. Which way does equilibrium lie here? Again, which is the stronger base, the alkoxide or the amide, the amine anion? Well, this is a stronger base, so what happens? This side is favored. Which is more basic, A or B? B is more basic because the non-bonding pair is not tied up in the aromatic system. A is aromatic. These two electrons are in the aromatic system because 1, 2, 3, 4, 5, 6. They're part of the aromatic pi system. Which is most acidic? Of course, it has to be one of the protonate amines. So if we look, it can't be either of these two. If I look at this, this, and this, I have to look at what's willing to give up a proton most easily. If I look at this amine and this amine, they're just going to make amines when they're through. And they're going to be somewhat basic and they can pick up the proton again. But when I take a proton off this, this will be aromatic. So this wants to get rid of a proton. So this will be most acidic. The amine conjugate acid has a pK of 10. So which side of the equilibrium is favored at pH 12? Well, the way that you think this through is you say pH 12 is higher pH than this, so it's more basic. That means there are going to be fewer protons than at pH 10. Fewer protons means the protons are going to be removed from this. So this side of the equilibrium will be favored. What is the outcome of this reaction? Well, what is this amine and the aldehyde going to do? They're going to form the imine. And then we have reducing conditions. What will that do? It will reduce it down to the amine, this amine right here. What is the outcome of this reaction? Well, this is one of those rearrangement reactions. The azide will make an acyl azide here. Then when you heat it, it rearranges, and water then protonates the hydrates the iso. What is A? Well, if I look at this, I know that this nitrogen, these are the conditions for Hofmann elimination. So this nitrogen must have been on this alkene. So it had to have been the nitrogen here or here. If I look, the 5-membered ring with the nitrogen attached, it has to be either this one or this one. If I look up here, how many carbons are around the chain to the nitrogen? 1, 2, 3. There's only 2 here. There's 3 here. So this was the compound. Which hydrogen would be most downfield? This hydrogen has 2 electron with is on a carbon that has 2 electron withdrawing groups on it, so that would be most downfield.